Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad KHAIRUL FAHIM ZAINAL. My matrix number is 16DE23F1010. Today we will present about the topic is Common Emitter Amplifier circuit. We'll begin with DC analysis to understand the biasing and operating point. Then we'll discuss the DC load line, which help visualize the transistor's behavior. Finally, we'll cover the AC analysis, including how to calculate the maximum input and output voltage. So we move to overview of a common emitter. Let's start with a brief overview of the common emitter amplifier. This amplifier configuration is widely used because of its high gain and versatility in audio and RF circuit. It consists of three main components. First, a transistor, which acts as the amplifier. Second, a biasing network, which ensures the transistor operates correctly. And last, a load resistor, which controls the output voltage and current. It's called a common emitter amplifier because emitter terminal is common to both the input and output circuit. After that, we move to DC analysis. Now, let's dive into the DC analysis. The purpose here is to calculate the question point or Q point. First, to do this, we calculate three key values. First, the base current is IB. Second, the collector current is IC. And the collector emitter voltage is VCE. So the first step, we use the Kirchhoff voltage law, KVL, for the calculation. Step 1, base the current IB. Using the formula is VBB equal to IB RB plus VBE. We can solve is for IB equal VBB minus VBE over RB. So step 2, collector current IC. Once IB is known, IC is calculated as IC equal to beta IB, where B is the current gain of the transistor. And the last step, collector emitter voltage VCE. Finally, using the collector circuit equation, VCC equal ICRC plus VCE. We solve for VCE equal VCC minus ICRC. This value together give us the Q point, the foundation for further analysis.
DC load line. Next, let's talk about DC load line. This is a graphical tool used to understand how the transistor operates across different conditions. The load line is derived from the collector circuit equation, VCC equal to IC per RC plus VCE. Here how we plot it. First, when IC equal to 0, VCC equal to VCE equal to VCC. This is the x-intercept. Second, when VCE equal to 0, IC equal to VCC divided by RC, and this is the y-intercept. By connecting these 2 points, we get the DC load line. The Q point is where the line interacts the transistor characteristic curve, ensuring the transistor stay in the active region.
Now let's move to the AC analysis, which is focused on the amplifier behavior for small input signal. Number 1 is maximum input voltage. The maximum input signal must ensure the transistor remain in the active region without clipping. This depends on the Q point and the swing limits within VOC and saturation. If VCE min equal to 0.2 volt, then the maximum VCE is equal to VCC minus VCE minimum. Number 2 is maximum output voltage swing. The output voltage swing is directly related to the input signal. To peak output voltage is VPP equal to 2 times VCE minus VCE minimum. For sinusoidal signals, the maximum output is half this value. Now, next is voltage gain, AV. The gain is given by AV equal to RC per RE, where RE is the transistor small signal emitter resistance. The conclusion is, number one, to summarize, number one, DC analysis helps us find the Q point. Number two, the DC load line visualize transistor operation. And number three, AC analysis ensures signal amplification without distortion. These calculations are vital for designing reliable and efficient amplifiers.